Bismillah Rahman Rahim. Today lecture is about the analysis and design of slab system. Uh, Topic of this whole lecture is organization of the lecture, analysis and design of one-way slab system, analysis and design of one-way joist system, analysis and design of two-way slab system with beams, analysis and design of two-way slab system without beams, mean flat and flat slab analysis, and the last one is analysis and design of two-way joist system. So all of these are related to slab. Some here one-way slab, two-way slab, and now the new topic is joist system. So this lecture is organized like analysis and design of one-way slab. Uh, as the ACI code approximate method of analysis called a strip method is used for the analysis of one-way slab, this topic has already been covered in BC lectures. And if still someone want to recall these lecture, they can go to Dr. Kesrali's website and just check BC lecture number 3 and 4. And you can also download this lecture from there. One-way slab design is a very simple and easy technique. It's just like a beam design. You have to cut a strip along the short direction and design that like a slab, a beam. Uh, Further, you can see the detail in the corresponding lecture number 3 and 4. Now, the second part of this lecture is analysis and design of one-way joist system. This topic will be covered in this lecture. After this, we have another topic, analysis and design of two-way slab system with beams. So the SCI code approximate method of analysis called as moment coefficient method is generally used for the analysis of two-way slab supported by step beams and walls. This topic has been covered in BC lecture number 4. So again, you can go there, Dr. Kesrali website, and you will have this procedure, moment coefficient method for two-way slab system. But again, in two-way slab, there are two cases, one with beams and another without beams. So moment coefficient method is generally applicable to the case when the slab is two-way and there is step beams or walls. This topic you can download from the website. Now, the final topic of this lecture would be analysis and design of two-way slab system without beams, mean flat and flat slab. So, the CI code approximate method of analysis called as direct design method. Mean this is the second part of the two-way slab system when there is no beams. So we will use direct design method for the analysis, the plate and plate slab. This topic has been covered again in BC lecture number 5. The student can download the same from the website. However, this topic will be quickly discussed in this lecture. So the first topic was analysis and design of one-way slab system, so that you can recall by yourself. The second type here is analysis and design of two-way joist system. So now this is the last topic, analysis and design of two-way joist system. We discussed one-way joist system earlier, and the two-way joist system will be discussed in this lecture at the last part. Therefore, in this lecture, only the following topics will be discussed: mean analysis and design of one-way joist system, analysis and design of two-way slab system without beams, and analysis and design of two-way joist system. So these three topics will be discussed in detail, and the rest one-way slab design based on strip method you can recall by yourself, and design of two-way slab system using moment coefficient method, you can also use this by yourself. So the first topic today, here I am recording the first topic, analysis and design of one-way joist system. So we will generally discuss this topic show some characteristics and basic steps for design along with serviceability requirement, and in the end we will do an example for this one-way joist slab system. So here is a one-way joist slab system. In the joist slab system, there exists beams, parallel beams, and above the beam there is a slab. And these small beams in turn supported by some primary step beams, uh, which will be designed separately. So the joist is a T-beam called joist are formed by creating wide spaces in what otherwise would be a solid slab. Joist construction consists of a monolithic combination of regularly spaced ribs in a top slab, mean T-beam or joist, arranged to span in one direction or to orthogonal direction. So this is a simple rib, and there is a slab, and then these ribs are supported by some step beams. So what actually this ribs working for us, because the normal procedure we constructing slab or beams. So what is the role of these ribs? These reps are have a function when the span of the slab is more, and I will give a range how much could be this, how much should be the span range for simple slab design and for joist slab system. So these secondary beams are indirectly you can call reps are used when the span of the slab increasing. ACI code 9.8 contains provisions for joist construction. I am illustrating the analysis and design of joist system as compared to regular slab system. A structure system will be, however, called as joist system if the pan width mean clear spacing between ribs. Between this is a rib and this is a rib. So distance between these two ribs we will call it pan width. So a structure system will be, however, called as joist system if the pan width is less than or equal to 30 inch. So when this pan width is less than 30 inch, we will call it joist system. This is a simple definition. If the system does not fulfill the requirement of joist system, then it shall be designed as regular slab beam system, which mean that slab shall be designed for plunger and beam shall be designed for plunger and shear, which is a routine case. Joist system is suitable for long span, as I already cleared it before, and it is economical between 30 feet to 50 feet span. Now, this is a clear distinction for those who working with the design in the field. So when the span increasing from 30 to 50 feet and you don't want any column or Doric, when you're using beam for 50 feet, it will have a long, more depth, and even the cost will be more. The system will have to be designed for more depth, and many things, the complexity will comes. So instead of these complexity, if the span is more, why not to convert this to a joist system, mean these ribs, and in turn these ribs will be supported by step beams. So that we will call it joist system. Some of the characteristics of a joist system is to the pan width, the pan width, reduce dead load. This means when we instead of using deep beams, the ribs have voids and it will reduce dead load. Second, electrical mechanical equipment can be placed between joists. Yes, there will be spaces between joist and you can place any of these electrical mechanical equipment. Uh, Third one is clear and unobstructed tenant spaces. Less effect of vibration due to stepper system. Yes, and the last one is standard form for the wide spaces between the reps are either 20 or 30-inch wide. So between the reps, the space should be from 20 to 30 inch and 8, 10, 12, 16 or 20 inches deep. So this is a simple range for the width and depth of the rep. Where it is should be used. So rep system is economical for buildings such as apartment houses, hotels, and hospital, where the live load are fairly small and the spans comparatively long. So this is another criteria for having a preference to joist system. And finally, palms are tapered in cross section, generally at a slope of 1 to 12 to facilitate removal. So the joist beams should not be like a rectangular, exactly like a rectangular beam. It should have a tapered section, because when you putting the palm work or shuttering below the joist system, it should have an ease of removing after having enough strength from the joist system. So the section of the rep should be tapered instead of rectangular, regular rectangular shape. Now, this was the general discussion about joist system. Now let's come to the design procedure of joist system. So the first step will be to assume dimension. So sizes of all structural and non-structural element are decided. This should be the first topic. Step. Second is to apply the loads. Load on structure are determined based on occupational characteristics and functionality. Occupational characteristics and functionality. This is as per building code of Pakistan. Every time we refer to these occupational character and functionality. Functionality and occupational mean, for example, we generally applying live load of 40 PSF, minimum live load of 40 PSF in residential buildings. So this is actually based on their functionality. Functionality mean this is a residential case, and so all the load defined in the codes is based on these characteristics. The third step will be the analysis, mean shear force and bending moment diagram. And the fourth step will be to design the system using or following some codes. These are the general steps. Now let's come to first step. From here we will decide depth and width of the joist system. So we already used this table 7.3.1.1 when we were designing solid one-way slab. If you remember, when we were designing, we haven't done this in the master, but you may have done that in the BC. So we were using this same table for the minimum depth of the slab in one-way slab system. The depth were for simply supported case, one end continuous, both end continuous, and cantilever. So we already used this first part in one-way slab system. Now here there was another row in the same table, beams are wrapped one-way slab. So they actually mean a wrapped beam actually mean the exterior beams. The exterior beams of the slab is called a wrapped beam. So the joist depth, the joist or the rep depth should be have value, minimum value to these things, depending on the supporting situation. Simply supported case, one in continuous, both in continuous and cantilever. So we will have minimum depth equal to this thing, and L is the span length, same as for solid one-way slab, and depth of the joist include slab depth. So for the case of joist system, the rep plus slab depth include in this depth. Normally, in one-way slab system, the depth of the slab were equal to minimum depth of slab were equal to this thing. But in joist system, this depth include depth of the rep plus the slab. Uh, how much will be the width of the joist? So minimum width of a rib will be equal to depth of the rib divided by 3.5, but not less than 4. So minimum width should be 4 inch, and the exact otherwise depth of the rib, which we discussed in previous slide, divided by 3.5. How much should be the slab thickness? So minimum slab thickness should be equal to clear distance between ribs, which normally we taking from 20 to 30 inch, divided by 12. But again, the depth of the slab in rib system should not be less than 2 inch. So here the limit is less. Generally, slab depth remain more than 3 or 4 inch in normal slab system. Here in rib system, it should not be less than 2 inch. Now let's come to loads. How much load we will apply? So one way joist system are usually designed for gravity load. Gravity load means 1.2 of dead and plus 1.6 of apply load. This is one of the combination of the ACI load combinations. And for a joist system, we will apply this simple combination. The joist lies for load per turning feet. Now let's see here. This is a simple joist system. This is a slab, and these are the ribs. And the whole of the system we can call joist system. Width of the rib between spacing between ribs. This is a rib. This is a rib. So spacing between these two ribs we will call it as width spacing, and this spacing will be equal to this thing. So if you taking between ribs or above the slab, it will be equal. It should be equal. Now this is a slab, a 3D style. These are the ribs. Here we have slab, and in turn, remember these ribs will be supported by some step beams. Now we are discussing only this thing, this rib. So for what we will do for analysis? For analysis, a single T-shaped joist is considered. This is a simple T-shaped joist, and this is along length of the joist. So we will consider only this section for analysis purpose, just like a T-beam. Now, for analysis, this table and one table more in the next slide is more important. So this is normally is for say approximate analysis. So this Ln is face-to-face distance between these step beams. Remember, these are the step beams. This is a step beam. This is a step beam, and here is a maybe you have column or end beam. So, and remember the ribs will be here. This is a span for the ribs. Ribs should be here. Ribs should be here so that the step beam can support these ribs. Remember, this first span between two step columns should be less than 1.2 times of normal span length or face-to-face distance between two step beams. Mean this span should not be more than 1.2 times of the remaining span length. Now this thing is important. Remember again, this is span for the ribs, and this is step beams. So the rib system is or the rib beam direct supporting by these step beams, and at the end we may have a spandrel beam or column. So both are possible. Spandrel beam means the end, the edges beam, the end beam of the slab or the corner beam of the slab is called spandrel beams. And support we will call spindle support. And if suppose at the end if there is a column, we can call it column support. Again, you should not be confused with the rep system. The rep system is from this beam to beam. Now, one thing more, we normally Now here, as we normally applying this formula, moment equal to W L square by 8. This is a very common formula, and it can be used for bending moment calculation in simply supported beams, and also in the case of slab, the boundary condition is for simply supported. Now, what we will do in this complicated system, we have step beams, and along with the step beam there are ribs beams, and there may be like this support here. This is a simple support, mean this is a roller or hinge support. And these are fixed supports. So how we will calculate bending moment in such situation? And also in case of fixed support, we there occur negative moment, and in mid span there is positive moment. So what we will do, how we will calculate bending moment, positive and negative in such situation? So the difference come only in the factor. Here we have used 1 by 8 factor along with the W into L square. So for the boundary condition, mean with the support, peg support, roller support, hinge support, only this coefficient varying 1 by 8. So here in this diagram, all these coefficients are given. If we calculating positive moment, so positive moment come in the mid span. So we will use this coefficient 1 by 14 multiply by L square W into L square. So this will be the coefficient, and this coefficient mean that one end we have spindle or column support, and other side we have this support, beam support. So we will use this. If for the both end we have fixed support on the beams, so we will be using 1 by 16 coefficient. And if one side is fixed and other side is a simple support, mean hinge or roller, we will be using 1 by 11 as coefficient for the positive moment. So these are the coefficient for the positive moment in such complicated system. What we will do for the negative moment calculation? So again, the same formula. Over the hinge or roller support, we will be using 0 coefficient, mean moment will be equal to 0. And here we will be using 1 by 10, and at this space we will be using 1 by 11, again 1 by 11, here again 1 by 10, and here 1 by 24 in case of spindle support, and 1 by 16 in case of column support. If suppose we have two spans, then we instead of using 1 by 11, 1 by 11, so we will be using 1 by 9. And if the span length is less than 10 feet, so then we will be using 1 by 12, this coefficient for the negative moment calculations. So this table is very important for calculating bending moments in such complicated systems. Now, design of joist for the flexure. Design of one-way joist is just like design of beam. Now, this is a simple model of joist. Here is continuous, here it is continuous, and this is a rib with the slab. This is called a joist. So, reinforcement for the joist usually consists of two bars in the positive bending region. Now, this is the positive bending region, because for the positive moment restriction, we using reinforcement at the bottom. So we will be using two bars. With one bar discontinued, we are no longer needed for or bend up to provide part of negative steel requirement over the support. Suppose if we have steel requirement here for positive steel is one bar, or near the support, if we putting one bar, so one bar should be bent up for the to the support for the negative steel requirement. One-way joists are generally proportional with the concrete provided all of the shear strength with no shear reinforcement. So this means that in one-way joist system, the shear will be provided with the help of concrete only. We will not calculate any shear reinforcement. So concrete requirement must be fulfilled through this concrete here. And we will do calculation in the example for this. Remember, this is positive steel and these dots are the negative steel for the ribs. And one which is perpendicular to this beam, joist beam, this bar is this. These are the slab reinforcement. And remember, location of for this reinforcement will be in middle of the slab, middle of the slab. So again, what I discuss is shown here. These are the joist positive bending steel, and it should be greater than what we minimum reinforcement of plug-in members. And these dotted are the negative bending bars, and this longitudinal bar, which lies perpendicular to this beam, is the slab main reinforcement. Now we have another type of reinforcement which is called skin reinforcement. Skin reinforcement, and as per this CI provision, that if the effective depth of beam or joist exceed 36 inches, the longitudinal skin reinforcement shall be provided as per ACI this section. So if the depth of the beam is equal to or greater than 36, not equal to, but if the depth of the beam increasing 36 inch, so we have to provide skin reinforcement. This is as per ACI. And the rest we will discuss an example about skin reinforcement. Now, maximum spacing requirement for plug reinforcement and slab. So, if spacing is obtained by plug demand, then compare spacing with 3H or 18, whichever is the less, we will use that one. This is the spacing for the slab reinforcement. For the main slab reinforcement. Now for shrinkage reinforcement, we will follow this pi time H or 18, whichever is the least will be the recommended space for the shrinkage reinforcement in the slab of joist system. Now let's come to shear. For the shear, if the demand, VU is the demand shear which lies at distance D from face of the support, where D is the effective depth of the beam. So VU normally come at a distance D from face of the support, and we calling it demand shear. So if the demand shear is equal to or greater than the capacity of the section, shear capacity of the section, then shear capacity shall be increased either by increasing the rep depth or width by providing single leg shear reinforcement. So mean if demand shear is greater than the available capacity, so we have to increase the capacity of the section, which normally we doing by either increasing the depth of the rep or width. And if the demand is less than the capacity, I mean shear capacity, then the section is safe against shear. Even minimum reinforcement is required for the beams. So here is a range, and we will discuss that in the next slide. Normally, you remember, if you recall shear design criteria for the beam, there were, if the demand is more than capacity, there were three ranges. In one range, there were required no shear reinforcement. In one range, there were required minimum shear reinforcement, and there was another range where no shear reinforcement was needed. So, if the demand is greater than half of the shear capacity and less than full capacity, mean the shear demand is greater than half of the shear capacity. Sorry, if the demand is greater than half of the shear capacity, so generally theoretically we mean this mean that if we have capacity and demand is greater than half of the capacity, so generally we saying that no reinforcement is required. But again, as per SCI, we have to provide minimum reinforcement, heavy minimum. Now, this slide generally mean that a minimum area of shear reinforcement shall be provided in all region where demand is greater than half of the capacity, except for the cases in the table. So we normally providing minimum reinforcement, shear reinforcement in such situation, but these situations are exceptional. Mean cases where AV minimum is not required. Normally, we provide minimum reinforcement in this range when the demand is less than the capacity but greater than half of the capacity. So, in this range, theoretically, we mean no requirement of shear reinforcement in the beam, but code saying that we have to provide minimum reinforcement in such situation when the demand is less than capacity and greater than half of the capacity. But there is some situation where we provide no reinforcement, shear reinforcement. Even if this criteria demand comes less than full capacity and greater than half capacity, still we will provide no minimum reinforcement. And one of these is shallow depth when the depth is less than 10 meter, 10 inches, and so on. So here is some situation, just read it out. And this situation, we will put no minimum reinforcement even if the situation is like this. Other than these situations, we normally provide a minimum reinforcement for shear capacity. Now, design for shear, the for joist construction, contribution of concrete to shear strength VC shall be permitted to 10% more than the specified as in chapter 22. So this actually means that whenever we calculating shear capacity of the section, so normally we will applying a factor of 0.65 or 0.75, but in case of joist, we will multiply a factor 1.10, mean 10% more than uh, what actual capacity is. So this is in case of joist system, we will have this situation. Critical shear section will be at a distance d from face of the support. This means that VU will be at a distance d from face of the support, where d is the effective depth. Now let's come to an example in all whatever we discussed here, we will clear in this example. Determine the required depth and reinforcement for the one-way joist system. The joists are 6-inch wide and are spaced 36-inch center to center. Mean between the two reps, the space is 36 inches and width of the one rep is 6 inch. The slab is 3.5 inch thick. So the slab above the rep is 3.5 inch thick. Fy is FC dash or FC prom is 4000 psi. Fy 60 grade steel. Service live load is 60 psi. Superimposed dead load is 64 psi. Width of spandrel beam. Spandrel beam mean exterior beams of the slab is 20-inch wide and interior beam are 36-inch wide. These beam mean the step beams, not the ribs. Ribs are here. These are the step beams of the whole system. Interior column dimension are 18 by 18 and exterior is 16 by 16. Story height is 13 feet. So this is the situation of what we want to go depth and reinforcement for one-way joist system. This is what we need to do. So it is a whole system, and length of this hall is 150 feet, and we have four bays, so each 30 feet. So five bays at the rate 30 feet equal to total 150. And in this direction, we have three bays, each 30 feet, and total is 90 feet. So this is a 30 by 90 by 150 feet frame system. And here we have these dash are the reps or joist system. And here we have these are the step beams. These are the step beams. So like here, and so we have total 6 step beams in this direction and 4 in this direction. Haji. Now, suppose I'm taking these three beams, this, and this. So this A section will be like this. See here again. Uh, this beam, which is a exterior beam, and this is a 20-inch width. So 8-inch from center to this side and 1 feet from this. So this total is 20-inch. And here this 3 feet means 36-inch. So interior beam width is 36-inch. And this beam is this one. And the rest is continuous. So between the two beams, we have spacing 30 feet, 30 feet, 30, and so on. So how much will be the face-to-face distance? Mean LN. LN just subtract 18-inch from this space and 12-inch from this, so it will be 27.5 inch. Now, remember, between these two beams, we have a rib system or a joist system. Here is the joist beam, and above this beam, there is a 3.5-inch slab. So the first step is we have to calculate sizes, and the same table we discussed here there. So we have deciding sizes for that part. So one end is fixed and other end is continuous. So depth of this will be equal to L by 18.5 inch. L by 18.5 inch. So just calculate L is 30 divided by 12, convert this to inches, divided by 18.5, and as per this, depth of the joist will be 19.5 inch. So 19.5 joist depth. So it will be because this depth already includes slab thickness. So slab thickness is 3.5 and 16 will be the rib depth. Now, out of this 19.5, if we how much will be the effective depth? So effective depth will be equal to just remove the cover, 3 by 4 inch cover and half-inch bar dia. Now using number 8 bar, so it will effective depth will be 18.25 inch. How much will be the width of the joist? Width of the joist already given in the question, 6 inch, and we have a check for the width of the joist, and it should be greater than rib depth divided by 3.5. Rib depth is 16, is from here divided by 3.5, so it will be equal to 4.57 inch. So this means we are within the limit. We used 6 inch and here we have 4.75, so we are on safe side. Now let's come to the load. This is a simple joist system slab, and this is a rib. Depth of the rib is 16 inch, 3.5 inch slab, and width of the slab, this rib is 36 inch, and total depth is 19.5 inch. So just calculate the dead load of this slab and rib individually. So area of this the rib is 6 multiplied by 16, 16. Our dead load will be equal to area of the rib multiplied by unit weight, which is 0.15. So it will be per unit length, it will be 0.10 kip per feet. Also, per foot dead load of the slab. So slab we have 3.5 inch and 36 inch width. So 3.5 divided by 36 divided by 144 mean convert this to square feet from inch square inch and multiply with the unit weight. So per running feet it will have 0.131 kip per feet weight. Also per foot superimposed dead load on the slab. So how much will be the total? Now in the question it is given that per feet superimposed dead load is equal to 64 psf. Now 64 psf superimposed dead load on the slab. So slab weight is 36 inch. Just calculate this is per square feet. So multiply 36. We will convert to per running feet. From per square feet to per running feet, just multiply the width, and we will get per running feet 0.192 kip per feet. Per foot live load on 36. So live load is given 60 psi. Now converted to per unit feet, it will be 0.18 kip per feet. Now find the total factor load, which is equal to 1.2 of dead load into 1.6 live load. Just put all these superimposed dead load and dead load of the system in self load plus live load. So it will have total load of the system in dead load and live load equal to 0.795 kip per feet. This is affected load of the system. Mean the whole revved system is a weight equal to W. W is equal to 0.7 something kip per feet. And we want to calculate how much shear force and bending moment come in these revved system or joist system. So these are the coefficients we already shown before. And just to calculate, put ln is given 27 point something feet and multiply with W is here, and these are the coefficients. So these are the positive moment coefficient and these are the negative moment coefficient. So just multiply these things and we will get this diagram. Suppose I want to calculate this from here, this value come 25.05 negative moment. So here is 1 divided by 24 multiplied by W equal to 0.7 something 795 and multiply by length equal to 27 p point something. So just multiply these things and we will get negative moment over here. Now for the positive moment at the center, again multiply W with the ln and with the coefficient of 1 by 14. So just multiplying these things, we will get all these negative and positive moment values. Remember, these value we will use for the design of the revved or the joist system. And for the shear can be shear diagram can be calculated easily. This is the 0.795 kip per feet UDL load, which is total factor load, and we have 27.5 feet span width, span length. So 0.75795 multiplied by 27 and divided by 2, that will be equal to 10.93, and 10.93 here. No. So total is 10.93. Then subtract this value. So it will be 12.57. Again 12. So just draw the shear force diagram using these load. Here is actually a difference in the span length. This is for 27 feet, 27.5 feet. So obviously the wheels will be a little bit up down. Now at this stage we already calculated the shear force and bending moment diagram using some with the coefficients, and also simple shear force can be calculated directly. Now come to design. We already done analysis. Now steps for design. The first thing is to exterior shear. Exterior shear is 9.72. This is exterior shear. VU exterior. Remember, VU always come at a distance D from face of the support. So the total maximum shear is 10.93, and this VU will come at a distance D from face of the support. So it will be 9.72. So exterior shear is 9.72 and interior shear is 11.18. See it again. Here, this is the total shear we use here, and VU at interior support, it will be 11.18. Now, what about the capacity? So capacity pi VC is equal to 1.10 multiplied by 200 root of C dash into TD. Remember, we had used, we already discussed this thing, that for the shear capacity in case of rep support joist system, we will be using we will be taking 10% more capacity. So 1.10 mean this thing, that we taking 10% more capacity than what come from this formula. So total capacity of the system is 11.42, which is greater than the demand, even this demand and this, both of this mean both of interior and exterior, so it's okay. Our capacity is more than the demand. Now come to the design for the positive moment. So positive moment, the effective width of the system we assumed is taken 36-inch center between the joist. Check if the joist is to be designed as rectangular or T-beam. So this is a common procedure. It take effect compression block depth equal to height of the flange and our slab, which is 3.5 inch. So put point AS value using mu divided by 5.2d minus a by 2. It will have a value of 0.57 inch square. Now again calculate A, and we calculate A by this common formula. A is divided by 0.85 c dash to be effective. So put value and come to be 0.27 inch. So this is verification that compression block compression block comes within the slab. Within the slab, we assumed initially 3.5, and now we calculated A is 0. So mean that we have a case of which rectangular. Therefore, design joist is rectangular beam. After trial, now we just proceed this trial because in rectangular beam we using the same procedure. Now just find out A is again using A is equal to this thing, and we will get A is equal to 0.53 inch square. Now convert number of bar used, so use number 5 bar, which is area equal to 0.6 because number 5 bar is 0.3 1 inch square, and 2 number 5 bar is equal to 0.6 inch and required is 0.5. So 0.6 will be on safe side. Now this is a positive steel. We will use at the bottom of the bottom longitudinal reinforcement of the joist. Now for the exterior negative moment we calculated was how much. It was something you can see, and width of the bottom width of the joist is 6 inch and depth is 19.5 inch and effective is 18 point. So after trials, these are the dimension. We have already the demand moment. Exterior demand moment is 25.05 cap feet. So just put value over there and apply the same formula. A is equal to mu divided by what? Mu divided by pi f y into d minus a by 2. So calculate A is after having some trial, we will get 0.31 inch square. And 0.31 inch square mean if you're using number 5 bar, so a single bar will work. And AS minimum is how much? This is the common formula for AS minimum. 300 root FC dash divided by Fy into BD should be equal to or greater than 200 by Fy into BD. So it comes to be 0.365, which is more than this. So in this case, we will apply the AS minimum, and AS minimum should. So it comes to be how much? Now remember, this negative reinforcement is for how much? How much width? The width of the top slab is we taken how much? 36 inch, mean 3 feet, and this reinforcement should be distributed over the 3 feet. So if you want per feet reinforcement, how much it would be? So if 0.365 inch square is over 36 inches or 3 feet, just divide by 3 and we will get per feet reinforcement area, which is 0.121 inch square. So we can use number 3 bar. Number 3 bar is area less than 0.2 inch square. 0.2 inch square is number 4 bar, so it will be less than. So just use number 3 at the rate of 10 inch center to center. Why 10 inch center to center? Because the total was 36 inch, and after deducting area of the die of the bar, we used number 3 bar. So on safe side, it may be 11 inch, but on safe side we can use 10 inch center. So along the length of the rep, for the negative reinforcement, we will be using number 3 bar at the rate 10 inch center to center, and positive steel we already calculated in the previous slide to number 5 bars. Now, design of interior negative moment. Interior negative moment. So interior negative moment mean that the moment come on the beam support, step beams. So again, the same procedure, just apply the moment, the AS formula, it will be this. Here now it's 0.36 and the minimum is 0.78. So just divide this by 3 because we want the total weight is 36 inch and our 3 feet and we want per feet will be 0.26. Just use number 3 at 5 center to center. Now just see here, these are the negative reinforcement on interior support. Interior support, we using the 3 bar at 5 in center to center, and for exterior support, they occur by 3 bar at 10 in center to center. This means that 1 bar from interior support will continue because an interior support there is 5 inch spacing reinforcement, and exterior there is 10 inch. So 1 bar will go to some distance from interior support, and it will not be continuous till the exterior. So 1 bar will be continuous and one will be discontinuous from interior to exterior. I mean the negative reinforcement. Now, design of slab. So for the slab, we know that these are the two loads, dead load and live load, and these are the loads, including this is the slab dead load and superimposed dead load and live load. So total load is 0.23 for the slab, and this is the slab system, 30 inch spacing, and this was the rib slabs, and these are the ribs beam. So over the support, negative moment coefficient will be 1 by 12 will be used. So mu will be equal to this thing. This is a very common formula for moment calculation, demand moment calculation. It comes to be how much? 0.12 kep per feet or 1.44 kep inch. So convert this into number of bars, it will be equal to 0.015 square per feet. Now AS minimum for this system, this is a very common formula for AS minimum, it have 0.08 inch square per feet. So we will be using number 3 bar at the rate 16.5 in center to center for this reinforcement. Remember, this is the reinforcement which lies perpendicular to reps beam, and the location of these reinforcement will be on the center of the slab. Now design of the slab for the flexure. How much will be the spacing for these reinforcements? So maximum spacing allowed for the temperature steel reinforcement is how much? This is should be 17.5 inch. So finally, we decide that these reinforcement should be at 16 inch center to center using number 3 bar. Here is a detailing. Just compare your details with the what we did. This is detailing for the slab, and here is the for the joist system. So this was the main bar, main reinforcement, and which we did in the last calculation, number 3 at 16 in center to center, and these are the negative reinforcement for the rep, and we did number 3 at 10 in center to center, negative reinforcement on the exterior support, and these are the positive reinforcement to number 5 bars. Should go all along. This should be on the exterior support. What will be the spacing between these bars on the interior support? Interior support will be 5 inch center, 5 inch. Now the new topic is analysis and design of two-way slab system without beams, flat plate. So this is you already did this topic in your bachelor when we were discussing punching, shear, and these like things. So let me do this thing, this lecture, record this lecture some other time because some students are waiting here. And let's see you again. Thank you.